In this video, I wanted to go over one of the examples that you'll find in the MPS Solved Problems. It's a basic causality assignment on a given bond graph. I'll go through the causality assignment, but then I'd also like to show you how you can use the bond graph editor software to build the bond graph and also apply causality and in that way determine the state variables as a simple example. So this is, I'm showing you here problem A-3-8 that you'll find, as I said, in the solved problems. Um, so this is simply just a given bond graph in generalized variables. I'm going to blow this up here so you can see it more clearly. And you can see it's got a source of effort, it's got an I element, a C element, and two resistive elements. So a straightforward kind of causality assignment if you've gone through some of the background on causality assignment of bond graphs. So we start off with the source of effort, and you would have applying that constrained causality on that source of effort. Once you're at that one junction, right, you're kind of free to then look around and look for other sources. There aren't any others, so we're going to jump right into the two energy storing elements, which we want to assign causality to first, right? So we can go ahead and assign integral causality on that I element, right? We're free to do that in this case. Once we do that, I trust you can see now that given that you've now given effort into that I element, sorry, I should be more clear on this side. It's effort, is specified into the I element. Then the flow is going to be known back into that one junction. So you can see that, right? How the flow is now determined at that one junction, which means that all the other bonds have to have effort being specified on that one junction, right? So remember, only one element, in this case, the I element that you've assigned effort into, now specifies the flow back into the one junction, and now flow is specified back into each of these elements. So you can see now these are all of these bonds are now, the causality is specified. So this causality is now specified going into this zero junction. Remember, at a zero junction, you can have as many bonds specifying flow, but only one of them can specify effort. So we're free now to choose that this other energy storage element, the C element, specifies the effort at that zero junction. Right now, the effort is specified at that zero, which makes sense. This is right the giving us now the effort into that R element. So note the two R elements have different causality. The I and the C each have integral causality, right, for those two types of energy storage elements. Remember, they're different for the I and the C. Since they both have integral causality, that means that our state vector, right, for this bond graph will be the momentum variable on the I element, the P, right, the momentum variable, and the Q, in this case, Q5. These are numbered bonds in this given bond graph. Okay, so now let's jump to the bond graph editor and see how you can use the software to do that for you automatically. I'm showing the bond graph editor here. Um, if you've played around with that, hopefully you've learned a little bit about how to use it. Um, uh, you can see the palette over here gives you all the basic bond graph elements, right? So we can start off and just go ahead and drop a source of effort down. I'm going to move this guy over here. Again, then the nice thing about how they've developed this is you can see, like, if you extend here, it'll tell you, you can now go on a pop-up here, and this is a one junction here, so I'm going to put a 1 there. It'll drop it for you. You can also do these and then basically put the bonds between the elements afterwards, but this is one quick way to do this. We have an I, which is reconstructed exactly the way it's built in this example. The I there, there's an R down here. Then on this bond, we're just going to a zero junction. And up above here, again, you could build it any way as long as you have the same bond graph. And down below, we have another R element. Sorry, the pop-ups are messing me up here. Okay, so now you've got all the elements. You can go ahead and now work with this. By the way, if you're going to do additional analysis, you can get a lot of those, and you can go through a quick tutorial on the Equalis website that gives you a quick start. But if you right click just here, you can see there's some functions that you can like. You can assign bond line numbers how you want. Again, left to right, right to left, however you want. Then we can auto assign causality. We can generate the state vector and generate a table of variables. If you're going to generate a table of variables, make sure that you've assigned whichever types of parameters you want. The nice thing about this tool is that you can either have linear elements, right? So we could specify for those given elements an I value or a C value, and do further analysis. All we want to do here is get the state equation. So I'm just going to show you first how to maybe do some initial annotation, and then we'll proceed from there. So first, let's go ahead and assign bond numbers left to right. Okay, and you can see it's now numbered them 1, 2, 3, and exactly. Actually, if you look at it, it's exactly the way it is in the example, which is fortunate. Now, if we're going to build a table of variables, then we would want to come in here and edit this I and give it an I element, and maybe give it an I underscore 2 or something. So you got to know a little bit about how LaTeX is. You don't have to, but it does help. When you double click on here, you see you're going to get this editing format here, and if you know a little bit about LaTeX, that shows a slash backslash BF means bold I. That's how it's being done in the background. And then what you want to do here is on that I, you want to put a colon, right? And then give it an I underscore for a subscript 2, because that's the second bond, and then just click outside of it, and you see now it's labeled it as having an I2. We'll do that for the same for the C here. We'll give it, that's a bond 5, so we're going to do a C underscore 5. We're going to go ahead and double click on this R, which is an R underscore 3, just to make these all linear. You don't have to, by the way, if you're building state equations, as we'll do in some other examples. These can all be nonlinear functions, okay? But just as when you go build a table of variables, it might give you a message that some of the variables aren't defined as linear. And let's just go ahead and do this as R6, okay, underscore 6. All right. So now we've got those. And here, this is it by default. These are going to be generalized variables, or the E's and the F's for the flow variables, and the P's and the Q's for the state, momentum and displacement variables. So let's go ahead and do that general. But you could go on here and label these if you wanted. So for example, I could come in here and double click on that. The first time you double click, it's going to give you an effort variable. So if I double click on that bond, you see it's very small. Over here on the right side, you'll see the font. I'm not sure if there's a way to make this in general default a little bit larger, because then it's kind of hard to see this. But I'm going to go ahead and see if I can click that up a little bit bigger. You see that, how it's growing? I want to make that bigger because my eyes, I need that help. I'm going to do an underscore 1. Like in the example, I have E1 of t, like a function of time. Don't do that here because it won't recognize that when it does the analysis. So this is an effort 1. It knows that that's a source of effort. I can now move that up in the top, right? Because that's an effort variable. So you can put that on there. And note that it's in red because it's not saved yet. If you want to work and you want to go ahead and save this to your device, for example, you could do that. I'm not going to do that for this example, but you could save it on device, or I think you can save it in the browser too. I normally save it into a file when I'm creating an example. So now that I've got the numbers, I've got some of these variables annotated. You could go in here and, for example, put, instead of having E2 here, you could put P dot 2 and so on. But it's going to by default have the momentum as a state. So let's go ahead now. You can right click. We've already assigned bond numbers. Now we can assign causality. And we just went through doing that by hand. Now you can see the nice aspect of this tool is you just say auto assign causality, and it's all been done for you. Isn't that great? So now you can go back and check. Remember, for this kind of bond graph that has explicit causality, everything is integral in terms of the storage elements. It should have a unique causality. Later on, when we look at algebraic loops or derivative causality, you might have different answers you could get. But here, this is going to be a unique answer. And you can also right click, and there's another, you can, what it'll do for you is generate the state vector, which we know it gives you the P2 and the Q5, exactly the way we've done by hand. Right. Now, the nice thing, lastly, we'll do this later when we start deriving state equations, and we'll do those by hand. But you can come back here, and this is what's so nice about this. To get state equations, right, that's not on here. There's a generated table of variables here. You can generate equations. Can you do that here? Those are all the equations that are present on this bond graph. Those aren't the state equations. Here is, for example, if you had functions, nonlinear functions, this gives you the constitutive equation. So, for example, this shows you that f2 for this I element is equal to I. So these are all linear. If you had nonlinear functions, it would show nonlinear functions. So those could be nice to have. And note, remember, this is based on a open source drawing tool, so you can actually paste pictures in here really nicely. And I'll show some other examples using the BGE tool here, where you can paste in, the actual system, for example, a picture, whatever, because this is the drawing package, so you can draw other stuff, but it's only going to analyze the bond graph. Again, very nice. So to get this actual state equations, which again, we'll do that some more later by hand before you use a tool. But just since we're here, go into Python here and say compute the state equations. Okay, and it's working. Please wait. There you go. So now it's actually, since it's a linear system, it's actually put it into state space form. Note that BGE gives it to you in sort of a reverse order of state space. And also this is shows a partial derivative, but this should be a total derivative. But here's your A matrix, your state vector, and here's your input, your B matrix and your input, right? Really nice to have that kind of automated state equation. You can actually copy this and paste it on here. You can do other things. You can copy and paste it directly into a LaTeX document for, to process it if you were going to create a document. So that's all for this example. Again, I'll have some additional examples to show you as we go forward.